Now that we know how to find derivatives using the difference quotient, we're going to talk about some basic differentiation rules, which is going to make differentiation a lot easier. First, we have the constant rule. The constant rule states that the derivative of any constant, or plain number, is equal to 0. So, if our f of x is equal to a constant, then the derivative of our constant is equal to 0. So taking a look at the first example, find the derivative of the following. A, our function y is equal to 8. Therefore, y prime, the derivative of y would be 0. For b, f of x is equal to pi squared. Now pi is just a constant. It's an irrational number. Therefore, the derivative of its constant is going to be 0 also. So f prime of x, just another way we can show derivative, is equal to 0. Our next rule with derivatives is the power rule. The power rule states that to take the derivative of a power, subtract 1 from the original exponent and multiply the result by the original exponent. Sounds a little more complicated than it is. So here's a very general example. You're given f of x is equal to x to the nth power. The derivative of that is actually going to be n times x to the n minus 1 power. Once you do some examples, you'll see that this is actually very simple. So the first question says to find the derivative of y equals x. We know that if there's no power there, it means that the x is being raised to the first power. So what we're going to do is we're going to take the first power, we're going to multiply it out front of the x. So our y prime, our derivative, is going to equal 1 times x to the 1 minus 1 power, as stated earlier in the power rule. So 1 minus 1 is going to give us 0. So we now have 1 times x to the 0 power. We should know by now that anything to the 0 power is simply 1. So the derivative of x to the first power is just 1. Let's take a look at our next example. Y equals x to the third power. We're going to take the 3, multiply it out front, so y prime is going to equal 3 times x to the, we're now going to take our original power, which was 3, subtract 1 from it, and it's going to be 2. So our derivative, y prime, is equal to 3x squared. Our next example is y equals the fourth root of x. Since our power rule with derivatives needs powers, let's rewrite this as a power. So this can be rewritten as y equals x to the 1/4 power. In order to take the derivative, we're going to apply the power rule. We take the 1/4, put it out front. So we now have y prime is equal to 1/4 x to the 1/4 minus 1 is going to give us negative 3/4 power. Now we don't like negative exponents, so we're going to take our x to the negative 3/4 and move it downstairs into the denominator. So our answer, y prime, is equal to 1 over 4 x to the 3/4. You can rewrite the x to the 3/4 using radicals and powers. However, it's not necessary as long as your power is positive. Looking at D, we have y equals 1 over x to the 5th. We don't know how to deal with powers if they're in the denominator. So we can take something from the denominator and move it into the numerator, by making its power the opposite. Therefore, y is the same thing as x to the negative 5th power. According to the power rule, take our exponent, move it out front, so y prime is equal to negative 5 times x to the, be careful with these negative exponents, if we have negative 5 minus 1, we're going to have negative 6. That's our exponent. Again, we don't like negative exponents, so let's move it into the denominator. Y prime is equal to negative 5 over x to the sixth. As you noticed in our last couple examples, sometimes you have to rewrite f of x so that it is written as a power. We need to rewrite radicals into rational exponents, and also rewrite fractions that have our x in the denominator into non-fractions with negative exponents. Our next examples ask us to find the slope of the graph of our function f of x equals x to the sixth, and an equation of the tangent line when x equals -1, and also when x equals +1. You'll notice that we only have an x value instead of an ordered pair like we did previously when we were trying to find an equation. Now, if I want to find a y value of my original function, if x is -1, let's plug in -1 into our original function, f of x equals x to the sixth, and find what the function value or y value would be. So when I plug in -1 in for x, -1 to the sixth power is +1. So our function value, our y value, would be equal to 1. So we now have the order pair -1, 1. Let's do the same thing for b while we're at it. Let's plug in our 1 for x so we can find what the function value or the y value is when x is 1. Well, 1 to the sixth power is 1, so we have the order pair 1, 1 for b. So now in order to find the slope and write the equation of our tangent line, we need to find the derivative. Previously, we used the difference quotient to find the derivative, but we now know how to use the power rule. So let's use our power rule and write our general form of our derivative, and then find the slopes at our specific points. So f prime of x, which we can use for both, is going to be, we have the sixth power, so we're going to move it out front. So 6 times x to the 6 minus 1 is 5. So f prime of x, the derivative, is 6x to the fifth power. To find m, our slope of our tangent line, when x is -1, I'm going to plug in -1 into our f prime of x function. So we have 6 times -1 to the fifth power. -1 to the fifth power is -1. 6 times -1 gives us -6 for m. So if I have a slope of -6 and the ordered pair -1, 1, we can write our equation y minus y1 equals m times x minus x1, and plug in the information. So y minus 1 equals -6 times x minus -1, which is plus 1. There's the equation of the tangent line when x is -1. Let's go ahead and finish b. We found the ordered pair earlier, so let's find the slope when x is 1 of our tangent line. To find our slope, we need to plug in 1 into our derivative. So m is equal to f prime of 1, which is equal to 6 times 1 to the fifth. 1 to the fifth power is 1. 1 times 6 is 6. So our slope for b is equal to 6. So now I have a slope, I have an ordered pair, so now I can write my equation. Y minus y1 equals m times x minus x1. So the equation y minus 1 equals 6 times x minus 1. Here's another rule that we can apply to derivatives. It's the constant multiple rule. If our function f of x is multiplied by a constant, we're going to take the derivative as we normally would with our power rule and multiply it by that constant. So let's take a look at our first example. F of x is equal to 3 times x to the fifth power. To take the derivative, f prime of x would be equal to 3 times, we take that 5, move it in front, so 3 times 5 times x to the 5 minus 1 is 4th power. All we need to do is clean it up a little bit. 3 times 5 is 15, x to the 4th. That's mathematically what we're doing. You'll start to apply this constant multiple rule right away in your head. Oops. So let's take a look at B. We have y equals 4 times the square root of x. We know that we need to rewrite the square root of x in a power. So we have y equals 4 times x to the 1/2 power. In order to take the derivative, we need to apply our power rule. So y prime is equal to 4 times this 1/2 gets multiplied out front, so 4 times 1/2 times x to the 1/2 minus 1 is going to give us negative 1/2 power. We need to take that negative power and move it down into the denominator and clean things up. So y prime is equal to 4 times 1/2 is 2, so 2 over x to the 1/2 power. If you prefer to write the 1/2 power as the square root of x, that's also okay. But again, positive fractional exponents are okay. Our next example looks a little more complicated than it actually is. First, we need to rewrite because we have a radical. So this can be rewritten as 1 over 5x to the 2/3 power. Now again, we don't like having our exponents in the denominator when we are applying our power rule, so we need to move it upstairs into the numerator by making it the opposite sign. So we haven't taken the derivative yet, so it's still y equals. We can make it 1/5 times x to the negative 2/3 power. So now to take the derivative, we're simply going to take our exponent, our power, multiply it out front. So we have y prime would be equal to 1/2, or 1/5, excuse me, times negative 2/3 times x to the negative 5/3 power. If we subtract 1 from negative 2/3, we're actually subtracting 3/3, which is going to give us negative 5/3. If we do our multiplication with our fractions, take our negative exponent, move it downstairs, we end up with y prime is equal to negative 2 over 15x to the 5/3 power. Piece of cake. Now we have a couple examples in table form, where it's walking us through the whole process of rewriting our function so it's in a form that we can differentiate using our power rule. Then the actual differentiation process, which is going to have some things that we must then clean up and have our simplified final answer. So for A, we have y equals 4 over 5x to the 6th power. So first, let's rewrite it and get that power out of the denominator. So it's going to be y equals 4/5 times x to the negative 6th power. Now we can differentiate. Let's take that exponent, multiply it out front. So now we have y prime is equal to 4/5 times negative 6 times x to the negative 7th power. Negative 6 minus 1 gives us negative 7. Now let's clean it up. Multiply the 4/5 times the negative 6. It's going to give us y prime is equal to negative 24 over 5, and our x to the negative 7th gets moved downstairs into the denominator to be positive. So our final answer, y prime is equal to negative 24 over 5x to the 7th power. Let's take a look at b. Y is equal to 9 over 8x to the negative 5th. Let's take our x to the negative 5th, pull it out, and make it the opposite. So our y is equal to 9/8 times x to the positive 5th. Now we're going to differentiate. Take the 5, multiply it out front, so y prime is equal to 9/8 times 5 times x to the 5 minus 1, which is 4th power. Clean it up. 9/8 times 5 is going to give us 45/8, and we have an x to the 4th. So y prime is equal to 45x to the 4th over 8. If you'd like, you could also write it as 45 over 8 x to the 4th, with x to the 4th off to the side. Looking at C, we have y equals x to the 5th plus 3x to the 4th plus 1 all over x cubed. This requires a little bit more rewriting than the others. So let's first take our denominator and put it into each piece of our numerator. So I'm going to rewrite down here first y equals x to the 5th over x to the 3rd plus 3x to the 4th over x to the 3rd plus 1 over x to the 3rd. Using some old-fashioned algebra power rules, x to the 5th divided by x to the 3rd is going to give us x squared, so we have y equals x squared. 3x to the 4th over x cubed is going to give us 3x, so plus 3x. And then 1 over x to the 3rd power. We don't like having powers in our denominator. We can't differentiate right now, so we need to move it upstairs into the numerator and make it x to the negative 3rd power. Now that it's rewritten, we can now differentiate. So our derivative y prime is equal to, take our 2nd power, move it out front, so 2x to the 1st power plus 3 times, there's an invisible 1st power, so 3 times 1 times x to the 0 power, 1 minus 1 is 0, plus, take the negative 3, multiply it out front, negative 3 times x to the negative 4th. Now we have to clean that up. Y prime is equal to 2x, 3 times 1 times x to the 0. X to the 0 is just 1. So 3 times 1 times 1 is just going to give us plus 3. And then we have minus 3 over x to the 4th. We have a negative 3, and then we took this x to the negative 4th, made it positive, and moved it into the denominator. As you observed in C above, the sum and difference rule for differentiation, in order to take the derivative of a sum or difference, we're just going to differentiate each piece of the sum or difference individually. So the derivative of f of x plus g of x would be the derivative of f of x plus the derivative of g of x. Same thing for subtraction. The derivative of f of x minus g of x would be equal to the derivative of f of x minus the derivative of g of x. Let's do a couple examples just to reinforce this. Let's take a look at A. f of x is equal to x to the 4th plus 12x. we're just going to differentiate each piece individually. So f prime of x, our derivative, is going to be 4x cubed, took our power, moved it out front, dropped it down one, plus 12 times x to the 0 power, which is 1, so just plus 12. That's it. Next we have b. F of x is equal to x cubed plus 3x squared minus 5x plus 1. We're just going to differentiate each piece. So f prime of x is going to be 3x squared plus, going to take this 2, multiply it into the 3, so 3 times 2 is going to be 6x to the first power minus 5 times that 1, which was invisible, so it's going to be minus 5 times x to the 0 power, which is 1, don't need it, plus the derivative of 1, the derivative of any constant, is simply 0. So our derivative for b is f of x, f prime of x, is equal to 3x squared plus 6x minus 5. We now have a few special derivatives that you have to take time to memorize. The derivatives of sine and cosine functions. The derivative of sine is equal to cosine of x. The derivative of cosine x is equal to negative sine x. Therefore, for our two examples, the first, y equals 3 sine x. The derivative of sine x is cosine x. Therefore, y prime is equal to 3 cosine x. For b, y is equal to 5x plus cosine x. We know we can differentiate each piece individually. So the derivative of 5x is simply 5, plus the derivative of cosine x is negative sine x. So plus negative sine x. We don't like to see those signs next to each other, so let's rewrite it nicely. Y prime is equal to 5 minus sine x. Our very last topic for tonight is a very important topic. That is about horizontal tangents. If a function has a horizontal tangent, then that tangent occurs where the slope, meaning our derivative, is equal to 0. So in order to find horizontal tangent lines, we need to calculate our derivative and then set our derivative equal to 0 and solve for x. Okay, this is going to be very important for us moving forward. As we just said, in order to determine the x value at which a function has a horizontal tangent line, I need to calculate the derivative and set that derivative equal to 0. So our derivative of a, y, is equal to x to the 4th minus 8x squared plus 2 is going to be y prime equals 4x cubed minus 16x. And then the derivative of 2 is simply 0, so it doesn't matter. Now, to find where I have a horizontal tangent line, where that x value is at the horizontal tangent line, I need to set my derivative equal to 0. So 4x cubed minus 16x equals 0. Now we're back into some good old-fashioned algebra and factoring. In case you forgot, I have that famous saying, when in doubt, factor out. So let's pull out a 4x. We are then left with an x squared minus 4 equals 0. Now a difference of squares, so 4x is equal to x plus 2 times x minus 2 equals 0. So in order for a product to equal 0, at least one of our factors must be equal to 0. So either 4x equals 0, x plus 2 equals 0, or x minus 2 equals 0. So those specific x values would then be x would equal 0, or positive or negative 2 in order for our derivative to be equal to 0. Let's look at part B. y is equal to 1 over x squared. In order to calculate the derivative, we need to take that x squared and bring it out of the denominator. So we have y is equal to x to the negative second power. To compute the derivative, y prime is equal to negative 2x to the negative third. Y prime is equal to negative 2 over x to the third. Now I want to set that equal to 0. But the problem is, running out of room, negative 2 over x cubed, can that ever equal 0? Are there any solutions? No, there are no solutions here, so there are no horizontal tangent lines. The last question for tonight is to use our answers from Part A to write the equations of our horizontal tangent lines. Well, we've established for B there are no horizontal tangent lines because it was not possible to have our derivative equal to 0. But for Part A, we had 3 different x values where our derivative was equal to 0. So there are 3 ordered pairs where a horizontal tangent line occurs. When x was 0, when x was positive 2, when x was negative 2. Just like we did earlier, I need to know the y value because horizontal tangent lines are y equals some number. So I need to know what is the y value when x is 0, what is the y value when x is 2, and what is the y value when x is negative 2. So we're going to take our x values and we're going to plug them back into our original function. So our original function was y equals x to the fourth minus 8x squared plus 2. When I plug in 0 into our original function for x, I then get my y value is equal to positive 2. When I plug in positive 2 for x, I get my y value is equal to 2 to the fourth is going to give us 2 times 2 is 4, times 2 is 8, times 2 is 16, minus 8 times 2 squared. 2 squared is 4, 4 times 8 is 32, plus 2. 16 minus 32 is negative 16, plus 2 is going to give us negative 14 as our y value when x is positive 2. Oops. Negative 14. When x is negative 2, we're going to get the same value as when x was positive 2 because of our even powers. Those negatives are going to be irrelevant. So, we established that we are going to have horizontal tangents when x is equal to 0, 2, and negative 2. However, horizontal tangent lines have the equation y equals a constant. So we must find those y values. Therefore, the equations for our horizontal tangent lines are y equals 2 and y equals negative 14.